Very good morning, students. In the previous class we are completing group 13 elements of p block elements. Today we are discussing new chapter, that is group 14 elements or 4th A or carbon family of p block elements of p block element. First topic, student, introduction of carbon family. Introduction of carbon family. The elements present in this group are carbon, silicon, germanium, tin and lead. Carbon, silicon, germanium, tin and lead. For each element, some interesting points we are discussing in this introduction. First element, student, carbon. Carbon is the 17th most abundant element in the earth crust. Carbon is the 17th most abundant element in the earth crust. First element, oxygen, silicon, aluminium, iron. Like that abundances we are given. The carbon is the 17th most abundant element in the earth crust. The carbon available in the earth crust in the form of coal, graphite, diamond in free form. In graphite, carbon is present. Diamond, carbon is present. Coal, carbon is present in free form. Whereas the carbon atom present in combined form in the form of hydrocarbons, carbonates, carbon dioxide in combined form. For example, hydrocarbons, alkenes, alkynes, aromatic hydrocarbon. In all these forms, the carbon is present in combined form, and also in the form of carbonate, sodium carbonate, magnesium carbonate, lithium carbonate, calcium carbonate. Some amount of carbon present in the form of carbonates also. And the atmosphere contains 0.03% of carbon dioxide. The carbon dioxide contains carbon in combined form. Carbon monoxide contains carbon in a combined form. Like this, the carbon is present in combined form in either free form as well as combined form. Next one, student, the carbon element available in the earth crust in the form of the three different isotopes. They are carbon 612, carbon 613, carbon 614. Three isotopes are available for carbon. Among these three isotopes, carbon 614 is known as radioactive isotope of hydrogen. The percentage of availability of this isotope in the atmosphere will be very less, because it is radioactive isotope of hydrogen. This isotope can be used in radiocarbon dating. That is, the age of the fossils can be determined by using radiocarbon dating. The age of the fossils can be used to determine radiocarbon dating or simply carbon dating. In objective question they will ask, which isotope used in radiocarbon dating? Carbon 12, carbon 13, carbon 14. Carbon 14 isotope is used. At the same time, age of Earth can be determined by using uranium dating. In the form of isotope uranium 92-238. Here the isotope using here is uranium 92-238. Comparative study is important, student. Carbon dating C14, age of fossils. Next, uranium dating, age of Earth, uranium 238 isotope. Clear, student? Next one, silicon. Silicon is the second most abundant element. In the earth crust. We know that oxygen, silicon, aluminium, iron, that is the availability of elements in the earth crust. The silicon is the second most abundant element in the earth crust. The silicon available in the earth crust in the form of silica as well as silicates in combined form. The glass and cement contains mainly silicon. Are the main constituents of glass and cement is silicon only. Why? Because cement contains sand. Sand nothing but silica. Silicon is Si. Silica SiO2. SiO2 nothing but sand. Sand is present in the cement. Similarly, glass also contains silica. Glass also contains silica. Therefore, the main constituent of glass and cement is also silicon. Si. Silicon dioxide, that is SiO2. Silicon is different. Silica is different. Silicon is the element Si. Silica is the compound of the silicon, that is SiO2. Okay, student. Next one. The ultra pure form of silicon can be used in semiconductors as well as transistors. The ultra pure form of silicon used in semiconductors as well as transistors. We know that the semiconductors are made from group 40 elements only, mainly silicon and germanium. Ultra pure form of silica are used in manufacturing semiconductors and transistors. Next one, student, germanium, third element, occurs in a trace amount. The germanium can be available in the earth crust in a trace amount, that is very small amount. The ultra pure form of germanium used in making transistors as well as semiconductors. Tin, which is known as stannum, The tin is available in the earth crust in the form of cassiterite, which is known as tin dioxide. In examination they will ask, cassiterite is a compound of which element? Tin or stannum. The lead is available in the earth crust in the form of the lead sulfide, which is known as galena. Galena is a compound of lead sulfide. It's a compound of lead, which is lead sulfide. Next, student, these group 14 elements possess mainly three types of properties. There are atomic properties, physical properties, and chemical properties. These three are we are discussing one by one. Okay, student. The first topic, introduction is completed, student, regarding the element. The first topic is atomic properties. In this subheading, we are discussing four subtopics. They are electronic configuration, atomic radius, ionization energy, and electronegativity. First subtopic, student, electronic configuration of the group 14 elements. Those are carbon, silicon, germanium, tin, lead. Their atomic numbers are 6, 14, 32, 50 and 82. Their electronic configuration are helium 2s2 2p2, neon 3s2 3p2, argon 3d10 4s2 4p2, krypton 4d10 5s2 5p2, xenon 4f14 5d10 6s2 and 6p2 are the electronic configuration. By observing all this configuration, the valency shell of each element contains same number of valency electron. 2s2 2p2, 3s2 3p2, 4s2 4p2 contains only 4 valence electron. Similarly, 5s2 5p2, 6s2 6p2 contain only 4 valence electron. Hence, the valency shell electronic configuration of group 40 elements generally represented as ns2np2, where n is known as valency shell period number or principal quantum number. Carbon belongs to second period. Hence n is equal to 2. Silicon belongs to third period. N is equal to 3. Germanium fourth period. Tin fifth period. Lead sixth period. Where n is known as period number, valency shell or principal quantum number. Copy this, student. Okay, students. Second property we are discussing, that is atomic radius. The atomic radius of the group 14 elements are as follows: carbon, silicon, germanium, tin and lead. Carbon is having 77 picometer, silicon 118 picometer, germanium 122, tin 140 and lead is 146 picometers. These are the atomic radius. Of the group 14 elements. Now you can observe, student, generally down the group the atomic radius will be increases. Here carbon to silicon, the atomic radius increases, much more increase like group expected. Okay. Next one, 118 to 122. Here the atomic radius increases, but the increase will be very small, 118, 119, 120, just 4 picometers will be increase. In a group, that much increase will be very less. Hence, here increase is observed but not expected increase. Similarly, from germanium to tin, here 122 picometer, here 140 picometer. Here also increases but not expected increase. Here 140 to 146 picometers. Here from germanium to the tin, the atomic radius even though increases but not as expected increase of atomic radius. The reasons are due to completely filled d and f orbitals. We know that germanium contains 3d10 and tin contains 4d10 and lead contains 4f14 and 5d10 orbitals. Due to presence of the completely filled orbitals, and these orbitals can act as a pore screening effect. Due to pore screening effect, the nucleus can attract the valence shell towards itself. Hence, the atomic radius will be decreases. In introduction, we are discussing that is in inert pair effect. Due to presence of 3d10 and 4d10 and 5d10 and 4f14 electrons in the heavier elements, they can act as a spook. They can act as a pore screening effect, and the nucleus attract the valence shell towards itself very strongly. Hence, the atomic radius increases but not increases as expected. Okay, student. Next one, ionization energy. The ionization of group 14 elements are as follows: carbon, silicon, germanium, tin, lead. 1086 kilojoules, 786 kilojoules, 760, 707 and 715 kilojoules. Generally, in a group, the ionization enthalpy will be decreases. From carbon to tin, as expected, the ionization enthalpy decreases. But tin to lead, the ionization enthalpy does not decreases. Instead of decreasing, increasing will be observed. That increase also very small. 707 to 715, nearly 8 kilojoules only increases. That is not a significant increase of ionization enthalpy. The reasons are due to pore screening effect of 3d10 and 4d10 in silicon and germanium in germanium and tin, and pore shielding effect of the 5d10 and 4f14 electrons in lead. Clear, students? Why the variation is observed in ionization enthalpies? Due to pore shielding effect of 3d10 and 4d10 electrons in germanium and tin, whereas in the lead due to pore shielding effect of 5d10 and 4f14 electrons. What happens as a screening effect is less strength, will be less strength. Due to weak screening effect, the nucleus tightly attracts the valence electron towards itself. As the nucleus attracts the valence electron very strongly, more energy is required to remove the electron, hence more ionization energy. Here from carbon to silicon, as expected, decreases because atomic radius increases. Here also ionization energy decreases as expected because atomic radius decreases. But here from germanium to tin, what happens here? Very less ionization enthalpy decrease is observed. Why? Because due to the pore shielding effect of the 3d10, 4d10 electrons in germanium and tin, as well as the pore shielding effect of the 5d10 and 4f14 electrons in lead. Clear, students? As the screening effect is strong, the nucleus does not attract the valence electron very strongly, hence less ionization will be required. As the screening effect is weak, due to presence of weak screening effect, the nucleus attracts the valence electron very strongly. If the valence electron very strongly, hence more energy is required. Hence the lead is having more ionization energy than the tin, because due to presence of very poor screening effect of the 4f14 and 5d10 electrons, the nucleus is strongly attracted. Hence the ionization enthalpy of lead is more than that of the tin. Okay, student. Next one, electronegativity. In carbon family, the electronegativity decreases as expected from carbon to silicon, but silicon to germanium, germanium to tin, the electronegativity is constant, that is 1.8. Whereas from tin to lead, the electronegativity will be increases instead of decreasing. Generally, in a group, the electronegativity value will be decreases, but here carbon to silicon only decreases. Silicon to germanium, germanium to lead is constant. Again, tin to lead, the electronegativity value will be increases. Here experimental values also there, student. 2.5, 1.8, 1.8, 1.8 constant, and 1.8, 1.9 the En value will be increases. These are the atomic properties, students, that is electronic configuration, atomic radius, ionization energy, and electronegativity. Next, student, second category of types of properties of carbon family, those are physical properties. First one is metallic and non-metallic nature. In group 14, carbon and silicon comes under non-metal category. Germanium is a semi-metal or metalloid. Tin and lead are metals. First two are non-metals. Germanium is semi-metal. Tin and lead are metals. It is about metallic and non-metallic nature. Next one, student, melting and boiling point in the carbon family follows a regular trend. That is, from carbon to lead, the melting and boiling point will be decreases. Next, third property, density, student. The density of the carbon family increases from carbon to lead because density is equal to mass by volume. Here mass means atomic mass. Atomic mass increases, density also increases. Density is directly proportional to atomic mass of that element. Hence, lead is having more atomic mass, more density. Therefore, the density of the carbon family increases from carbon to the lead. It is about the physical property, student. Third topic in this carbon family is chemical properties. In that, first one is reaction with the air or oxygen. When these elements react with oxygen, it can form two types of oxides. They are monoxides and dioxides. Monoxides general formula EO. Dioxide general formula EO2. Where E is known as element, carbon, silicon, germanium, tin and lead. Where E is known as elements of the carbon family. Let us consider monoxides. That is carbon monoxide, silicon monoxide, germanium monoxide, tin monoxide and lead monoxide. The nature of these oxides will be as follows. Carbon monoxide is a neutral oxide. Silicon oxide exists at a high temperature. And germanium oxide is acidic oxide. Tin and lead oxides are amphoteric oxides. In examination, the last student arrange the oxides classify the oxides into acidic, amphoteric, basic oxides. At that time, it will be useful. Neutral oxide exists at high temperature only. Acidic oxide as well as amphoteric oxides. Next one, student, dioxides. Carbon dioxides, silicon dioxide, germanium dioxide, tin dioxide and lead dioxide. Carbon and silicon dioxides and germanium oxides are acidic oxides. The dioxides of carbon, silicon and germanium are acidic oxides. Whereas tin dioxide, lead dioxides are amphoteric oxides. Clear, students? Right. Next one. Second chemical property, with water or steam or hot water. Carbon, silicon, germanium never react with the water molecule. There is no reaction of these elements with the water molecule because of their passivity. That is, when water molecule approaches carbon molecule, there is no reaction. When carbon is added to water, before addition of water, same thing. After addition of water, same thing. That is no reaction. But when tin can react with hot steam or hot water, it can form tin dioxide plus hydrogen. Where tin dioxide is known as special name, that is cassiterite. In the introduction we are discussing. Cassiterite is known as compound of tin, that is known as tin dioxide SnO2. Whereas lead react with water, there is no reaction. Why? Because due to formation of the protective oxide film. When lead is added to water, immediately around the lead some oxide film is formed due to formation of the lead oxide. This lead oxide, protective oxide film, prevent the further reaction of the water molecule. In examination, they will ask student, why lead does not react with the water molecule? Due to formation of protective oxide film around lead. protective oxide film around lead. Copy this, student. Okay students, next topic in the chemical properties, oxidation state. Oxidation state. We know that the real or apparent charge present on the atom in a molecule are known as oxidation state or oxidation number. The group oxidation state of carbon family will be +4 because which contains only 4 valency electrons. Other possible oxidation state is +2, which is 2 units less than the maximum oxidation state. The other possible oxidation state is 2 units less than the maximum oxidation state or group oxidation state +2 because of inert pair effect. We know that according to concept of inert pair effect, the reluctance of NH2 electron to participate in chemical bond formation are known as inert pair effect. Due to this effect, down the group, higher oxidation stability decreases, lower oxidation stability will be increases. For more clarity, previous videos once you can observe, student, inert pair effect clearly we are discussing. Next one, student, the carbon and silicon shows +4 oxidation state. The carbon and silicon shows +4 oxidation state, and the carbon also shows -4 oxidation state also. Because carbon is the first element in the group. Carbon is having highest ionization enthalpy. To form +4 oxidation state, 4 electron it can losses. Therefore, 4 ionization energies are required. We know that carbon is having highest ionization energy. Due to highest ionization enthalpy, much more amount of energy is required to form +4 oxidation state. Therefore, instead of losing 4 electrons, carbon is ready to gain 4 electrons also. If gain electrons -4 is possible, hence it can get the stability. The electronic configuration of carbon is 1s2, 2s2, 2p2. 2s2, 2p2 is 4 electron. If another 4 electrons are present, it can get the stability. Instead of losing electron, carbon also shows gaining electrons. That is, carbon shows -4 oxidation state also, because carbon is having highest ionization enthalpy. More energy is required to form +4 oxidation state. Next one. Germanium can form stable compounds in +4 oxidation state and only few compounds in +2 oxidation state. The germanium can form very stable compounds in +4 oxidation state and only few compounds in +2 oxidation state. That is, here +4 and +2 is possible, but +4 is more stable, +2 will be less stable. That is. Next one. The tin can form +4 and +2 oxidation state form compounds. The next element is tin. Tin can form compounds in +4 as well as +2 oxidation state. Next one is lead compounds in +2 oxidation state are more stable than +4 oxidation state. Down the group, the +2 oxidation stability increases. For lead, +4 and +2 is possible, but +2 will be more stable due to inert pair effect. Hence, if lead is present in +4 oxidation state, it is ready to convert into +2 oxidation state, because lead in +2 form is more stable than +4 form. The lead +4 can be converted to lead +2 by the gain of 2 electrons. Therefore, lead +2 is formed. Here we know that gain of electrons are known as reduction. The substance which gains electrons are known as strong oxidizing agent. In competitive point of view, they will ask why lead element can act as strong oxidizing agent. Due to inert pair effect, the lead +4 can be converted into lead +2 because lead +2 will be more stable, and lead +2 can act as a strong oxidizing agent. Next one, student. The hydrides of these elements are electron precise in nature because they are having 8 electrons around the central atom. Hydrides, the compounds of hydrogen with the other element are known as hydrides. The binary compounds of hydrogen with other elements are known as hydrate. Here, when the group 14 element react with the hydrogen, it can form hydrates of general formula EH4 because plus 4 is the group oxidation number. Here, these hydrates are electron precise in nature. Electron deficient means they can require electron. Electron rich means they can donate electron. Electron precise means they are neither deficient nor electron rich. Around carbon, exactly 8 electrons are present. Exactly 8 electrons are present. Hence, it is an electron precise. It does not require any electron to get stability. Therefore, the hydrates of the group 14 element are electron precise in nature. Electron precise in nature. For example, in the group 13 elements BH3, the hydride of boron BH3 can exist as a dimer because it is having less than 8 electrons. BH3 means 3 boron hydrogen bonds, 6 electrons, less than 8 electrons, that is electron deficient hydride. Electron deficient hydride. Less than 8 electron deficient. 8 electrons, electron precise. More than 8 electrons around central atom, that is electron rich. Here, the hydrates of group 14 elements comes under category electron precise in nature. They neither require electrons nor donate electrons to the other species. Exactly 8 electrons are present. Here, student, it is about oxidation state. It is about oxidation state. Next property, student, reaction with the halogen. When group 14 elements react with the halogen, what are the product form? When elements react with halogen, it can form dihalide as well as tetrahalide. Two types of halides are formed, EX2 as well as EX4. Where X stands for halogen, fluorine, chlorine, bromine, iodine. Astatine is a radioactive element we are not considering. E stands for element from carbon to lead, carbon, silicon, germanium, tin and lead. Here regarding EX4, first we are discussing, student. EX4, tetrahalide. The tetrahalides are covalent in nature, sp3 hybridization and tetrahedral shape. All the tetrahalides are having covalent in nature, having sp3 hybridization and tetrahedral shape. Except some exceptions are there. Those are tin tetrafluoride, lead tetrafluoride are ionic in nature. Why? Because the fluorine is having highest electronegativity and lead can show +2 oxidation state, tin can show +2 oxidation state. Therefore, the tetrafluorides of tin and lead are ionic in nature. And one very interesting point, student, in examination expected question, the tetraiodide of lead does not exist. EX4 is possible, but tetraiodide of lead does not exist because PbI4 can be dissociated or decomposes into lead diiodide plus iodine molecule. Lead diiodide plus iodine molecule. Because in tetraiodide, lead can exist in +4 oxidation state. Here we know that lead +4 can act as strong oxidizing agent, readily converted into +2. Therefore, tetraiodide can be converted into diiodide plus iodine molecule will be evolved. This is due to presence of the inert pair effect, and lead +2 is more stable than lead +4. Down the group, what happens, student? Higher oxidation stability decreases, lower oxidation stability increases. Here down the group, +4 oxidation state stability of the group 14 element will be decreases, whereas +2 oxidation stability of the group 14 elements will be increased due to inert pair effect. That is, carbon is more stable in +4, lead is less stable in +4. Carbon is less stable in +2, lead is more stable in a +2. Down the group from carbon to lead, +4 oxidation stability decreases, +2 oxidation stability increases due to inert pair effect. Here lead iodide, that is lead is present in +4 form. Lead diiodide, lead is present in +2 form. We know that when compared to +4, +2 is more stable. Due to this reason, due to this inert pair effect, lead tetraiodide can form lead diiodide. Next one, student. Carbon tetrachloride does not undergo hydrolysis, because due to the absence of d orbitals, Carbon does not contains any vacant d orbital, hence the carbon tetrachloride does not undergo hydrolysis. Similarly, silicon tetrachloride upon hydrolysis it can form first of all one chlorine can be replaced with the hydroxy group minus HCl and 3 chlorine atoms are present. It further react with water molecule. It can form silicon tetrahydroxide, which is known as silicic acid. Therefore, silicon tetrachloride upon hydrolysis it can form silicic acid, which is known as silicon tetrahydroxide. Okay, student. Next one. The stability of the dihalides increases down the group. The stability of the plus 2 oxide stability increases according to oxidation constant. Hence, the stability of the dihalides will be increases. For example, lead dioxide is more stable than lead dihalide is more stable than lead tetrahalide because of inert pair effect. Down the group plus 2 oxide stability increases. Whereas germanium dihalide and germanium tetrahalide, the tetrahalides of germanium can form more stability than dihalides of germanium. Therefore, germanium dihalides are less stable than germanium tetrahalide. Clear, student? It is about reaction with the halogen. In this one, the main important thing expected question is why carbon tetrachloride does not undergo hydrolysis due to absence of vacant d orbitals present in the carbon atom. Copy this, student.